Swayam Prabha. Digital India. Educated India.
Hello dear friends, welcome to this lecture of Module 1 on Advances in Engineering Geology. In previous lectures, we have discussed about rock material and rock strata in brief, concept of stress, deformation, strain and stress-strain behavior in brief. Now in this lecture, we will elaborate about stress-strain characteristics of rocks, mode of failure, and in brief about the mechanical parameters. In this lecture, we are going to discuss about stress-strain behavior and mechanical parameters in brief, which will be elaborated in our future classes further. In this class, we are going to cover about stress-strain characteristic in detail, basic geomechanical parameters, deformation property and types of failure, concept of strain, modulus and Poisson's ratio. As you know, when we are going to stress any rock body or any type of body under compression, then we can see here if we are going to compress this by applying load in form of stress, then there is a deformation in this body, and the deformation can be measured in form of strain. And strain, as we have already discussed, it may be linear, it may be area or aerial, it may be volumetric. First, we are taking the example of linear for an easy understanding. As far as strain characteristics are concerned, this characteristic of geomaterial, particularly in case of rocks, is actually representing the response of rocks with respect to external cause or external forces. It may be natural, it may be anthropogenic. If we are going to plot the value derived in form of strain, which is we have already discussed, that is the change in length divided by original length. Later on we will discuss about the time dependent deformation under constant or incremental position. Here we have already plotted the stress and strain, particularly through axial strain and stress measurement. This experiment was carried out by me. If we are going to see here the increment in stress-strain behavior, when it is 0, there is no strain at 0 stress. When we are going to put this stress 1 MPa, then there is a strain of some limited value. When we are going to put this 5 MPa, then there is a corresponding development of the strain. Progressively, there is an increment in stress and there is an increment in strain. If we are going to see overall the view, stress-strain characteristic of rocks, then we can say that this overall pattern of the stress-strain is actually non-linear in nature. Why non-linear in nature? Because the rock is inhomogeneous and anisotropic in nature. On one side, another side there is a continuous change in internal response with respect to external cause. If here we try to analyze this stress strain curve, we can see this type of non-linear zone. And this type of non-linear zone, if we see here, with decrease in strain rate, so there is increment in strain with respect to stress, and it is a curved in nature. With respect to this x-axis, it is concave in nature, and this concavity is due to collapse of voids, pores, cracks, and fractures present in a rock. After complete closing of voids, cracks, pores, fracture present in a rock, there is increase in stiffness of rocks. So this portion between this point to this point is representing elastic. When we are going to see, actually by drawing this tangent on this stress strain line, then we can say that now stress strain behavior started departing from this linearity and again become non-linear. This point which indicate the behavior of stress strain departing from the linearity is recognized as yield point. Further, in progress of deformation and increment in stress value, there is a further deformation in non-linear fashion. With respect to this x, we can say that we are getting concave type of geometry of the stress strain curve. This concave type of geometry indicating there is increment in strain. This peak point technically we are going to recognize as failure point. So we have discussed about, if we are going to see here the departure from the linearity, compaction point, phase of departure we are recognizing as yield point, and the maximum reach of the stress strain curve in term of the stress is recognized as the peak point. Thereafter there is a gradual fall in stress strain behavior. Here we can see this rock is still showing some resistance to failure, or having some ability to resist the present stress in the sample. This zone is characteristic rocks based on stress strain characteristic after peak. We are going to divide this stress strain curve taking this position peak point. This region before peak point means pre-peak. As the peak we are recognizing to declare as failure of rock, therefore we can also recognize this zone as pre-failure zone. After peak point or after failure point, then we can say that this is the post-failure region, and having some value here peak point. If we are going to see this value by drawing this line on stress axis, then we can say that this is the maximum stress. This is the maximum stress which can be easily beared by a rock. This point representing the peak and the value of stress is the maximum stress that can be attained by a rock. This capacity of rock or maximum stress value, this stress is a maximum stress and this is the capacity of a rock. Immediate reach to the zero stress. It means this indicates about some strength present in rock. Therefore, this type of capacity or stress is due to residual. If we are going to see this stress strain curve, this stress strain curve for identifying different type of mechanical parameters, then we can easily identify different parameters based on the stress strain characteristic. Therefore, stress strain characteristic is a very important for analyzing overall response of rock with respect to external cause or external changes or external stress. Maybe natural, maybe of anthropogenic. If we are going to see mechanical parameter is strength, modulus and Poisson's ratio. This Poisson's ratio after Sir Poisson. Now if we are going to see about the strength, we can say that the strength is the value of maximum stress attained by a rock before failure. This value of stress at failure point is recognized as strength. This strength is a maximum capacity of rocks, maximum stress value that can be sustained by a rock. It is a capacity to resist an applied stress. This peak strain of rock is not ultimate failure. Still, there is some strength present in rock, and this type of strength, minimum value of the strength present in rock, we are going to recognize as residual strength or remnant strength present in rock. And the rock in this zone after peak is useful in studying the different mode of failure for proper planning and design of support system in highly fractured rock or highly deformed rock. Therefore, the post-failure characteristics in view of stress strain behavior is also very important. If we are going to see the failure of rocks in view of the brittleness, then we can say that the failure of rocks occurs principally in two modes. One is a brittle failure and another is ductile failure. One is a brittle failure and another is ductile. In between these two, we have a term semi. So, in between these two, partially brittle, partially ductile, we can say that semi-brittle or semi-ductile failure. The brittle failure is the process by which there is a sudden loss of strength across a defined surface without permanent deformation, and this permanent deformation we are recognizing as the plastic deformation. This sudden loss of strength is characteristic of brittle failure, and this type of failure is representing by the development of brittle fracture. However, in case of ductile failure, there is no such type of sudden loss. There is continuous deformation without failure. This type of failure we are able to observe in case of metals or in case of some other synthetic material. In case of rocks, we are going to expect such type of failure at higher temperature. As we have already discussed, the stress-strain behavior departing from the linearity or elastic zone, then we are going to recognize as the yield point, and this yield point is representing about the increment in deformation other than the elastic deformation, non-elastic deformation, and the corresponding value of this yield point is recognized as yield strength. Then further, in progress of this stress-strain behavior, the peak point or failure point and the corresponding value of this stress is recognized as strength or failure strength. Now, another term is a modulus. The Young's modulus is a very famous in case of metals, in case of ceramic, in case of general material science or material. This modulus, under the term this Young modulus, is defined as the axial stress and consideration of corresponding strength. It means it is the ratio of axial stress to the corresponding strain below the proportional limit under stressing. What is the proportional limit? Proportional limit means within the elastic region, not beyond the elastic region. Therefore, the Young modulus in case of our study, we are going to recognize as the modulus of elasticity. Modulus of elasticity. Because we are going to measure the modulus within the elastic zone of stress-strain characteristic. If we are going to see the Poisson's ratio, the Poisson's ratio as per concept is a ratio of transverse strain or lateral strain with respect to axial strain within the proportionality limit of under stressing or within the elastic limit. If the stress is not compressive or tensile belonging to the shear mode, then the same concept, ratio of shear stress to the corresponding shear strain, is recognized as shear modulus. And in practice, traditionally we are using the letter G for the shear modulus. The shear modulus is also known as modulus of rigidity. It means if we are going to see this modulus of rigidity, we can say that the rigidity is always measured under shear mode. It is equally applied on rock as well as in living walls also. Besides shear modulus, we have bulk modulus, and bulk modulus is a very simple, as we have already discussed in case of the modulus of elasticity, shear modulus. Similarly, here the ratio of hydrostatic stresses with respect to change in volumetric strain. It means ratio of hydrostatic stress or pressure and volumetric strain. If we are going to see this shear modulus, we can say that we can establish one relationship recognizing E is equal to 2G 1 minus nu, where nu is representing Poisson's ratio, is equal to 3 bulk modulus 1 minus 2 times Poisson's ratio, and we can see this here overall relationship 9 kg by 3 k minus g, where k is representing bulk modulus, g is representing modulus of rigidity or shear modulus, and these are the some numeric values. So in this way we can able to estimate technically some numerical values for this E if we are knowing this k and g, or if we are able to know k and this Poisson's ratio nu. This Poisson's ratio we are representing by this nu term, this modulus of elasticity by E term. Here I try to elaborate these things based on our description regarding stress strain behavior, how we are going to see. If we are going to leave this portion, here try to draw this line tangent on this stress strain behavior, then the value of this stress representing this elastic zone and the corresponding value of strain, because this is the elastic zone, then there is a law of proportionality. There is increment in stress, then there is increment in strain, and this relationship is represented by the slope of this line. The slope of this line, we can say that the slope of this line we can define this is the ratio of stress by ratio of, if we are using this symbol for the strain, ratio of stress, change in stress and change in strain. This ratio of stress and strain we are going to define by one letter E, and this E is representing the modulus of elasticity. If we are going to see the unit concerned to this change in stress we are going to measure in kg per cm square, or in another unit Pascal, or bigger unit megapascal or kilopascal, etc. So if we are going to see here these two, this delta sigma or the stress is represented by this PA or kPa or MPa, Pascal, kilopascal or megapascal or gigapascal, and as per our earlier discussion, the strain is a change in length by total length. Here the dimension is here L, also dimension is L, and therefore L crosses L and becomes 0. It means the strain is a dimensionless. Therefore, the unit of the modulus of elasticity is also same as we are going to observe in case of, or note in case of the stress. So this, the unit is also MPa or PA or kPa or kg per cm square. This portion representing the elastic region, and there is a deviation from the elastic. This point is recognized as yield point. Therefore, the corresponding value, if we are going to draw this line on stress zone, then we can say that this point, this value of stress is actually yield stress. And the corresponding value of strain is yield strain. Further, there is increment in stress due to applied increase in stress, and there is increment in strain, and this we are going to declare as a peak point or failure point, and the corresponding value of this stress, is recognized as peak stress or failure stress or simply strain. This strength is also having the same unit as we are going to observe in case of stress. So also Pascal or kilopascal or megapascal or gigapascal. Then this region, time to time we will discuss in our future classes also, is a post-failure region where we are going to see the development of different failures and make this region as a failure region. This corresponds to the fracture ground, as we have already discussed. Characteristic of fracture ground which require moderate preparation and high level of treatment. If we are going to see further here, this is the stress-strain curve based on the measurement of axial strain, and axial stress. This axial strain and axial stress is representing the modulus within this zone. If we are going to see the changes, suppose this is the sample, cylindrical sample of rocks. Here there is a change in this axial direction and change in lateral direction. When we are going to compress this, then the sample may be like this, rock sample may be like this. So there is a change in lateral or transverse direction and there is a change in axial direction. So axial direction, the change in strain with respect to incremental strain we have plotted. The lateral strain, if we are going to plot this lateral strain also, is like this. Then we can say that this change in lateral strain, if we are going to draw this perpendicular here, going to draw this perpendicular here, and going to draw this perpendicular here for this region and perpendicular here. So this psi 1 and this psi 2, if we are going to see this psi 1 and psi 2 and following the concept proposed by Sir Poisson's, then we can say that this Poisson's ratio nu is equal to ratio of this lateral strain, this delta psi 1 and this delta psi 2. This is the axial strain and this is the lateral strain or transverse strain. So ratio of the lateral strain and axial strain, but measured within this region of elasticity or within the limit of elastic region. So the modulus of elasticity, as the name indicates, and Poisson's ratio, both are characteristic of elastic region only. After this region, after yielding, there is a departure from linearity and this stress strain characteristic become non-linear. Then reaches this peak and corresponding value of stress that represent the maximum capacity of rock to bear. An applied stress or applied cause is recognized as strength and measured in ampere. If this curve we are going to assume under shear stress mode, then this value, corresponding value of this stress and corresponding value of this strain, if we are going to see this G, modulus of rigidity, then we can say that shear stress, generally represented by this letter tau, divided by corresponding shear strain represented by this gamma, is considered as the shear modulus or modulus of rigidity. If we have having experience or value of this shear stress, corresponding shear strain, then we are able to calculate the modulus of rigidity easily. And if we are having the stress change within this elastic limit and this corresponding strain, then we can say that this corresponding strain, then we can say that this is the modulus of elasticity. In case of this three-dimensional consideration, in triaxial stress condition, there is a change in surrounding stress condition or resultant stress condition, devoteric stress, and then change in volumetric strain we are going to recognize as the bulk modulus. So, friends, in this brief, we have already discussed about the different modes and different characteristics of the stress strain behavior. This aspect can be well studied through this engineering geology book written by Well and written by the Waltham and written by the Vasavalu. Friends, if we are going to conclude this brief discussion, then we can say that the stress strain characteristic is representing the mechanical response of rock. The rocks are non-linear in deformation behavior due to anisotropic and heterogeneous nature of rock. The modulus is a ratio of stress and strain applied in all cases if within the elastic limit applied for the axial change in stress and strain, then it is a modulus of elasticity. If the mode is a shear mode, then the ratio of the shear, stress and strain recognized as modulus of rigidity. And if there is a deviatoric type of stress and corresponding change in volumetric strain, then this ratio we are representing as the bulk modulus. The Poisson's ratio is the ratio between the transverse or linear strain and axial strain measured within the elastic limit of a rock. And the failure generally occurs in form of brittle failure, ductile failure, and in between these two, semi-brittle failure. Dear friends, in this class we have discussed about concept of geomaterials, concept of stress strain characteristic, about different mechanical parameters, concept of stress, concept of strain, concept of modulus, representing different type of modulus as modulus of elasticity, shear modulus or modulus of rigidity, bulk modulus under triaxial stress condition and uniaxial stress condition. Then we have discussed about the mode of failure, particularly brittle failure, ductile failure, and in between these two, semi-brittle failure. Then we have discussed about the Poisson's ratio, that is the ratio of the lateral strain and axial strain. These basic parameters will help to understand our future classes regarding advances in this direction. Thank you.